Hello, there was a problem with the audio for today's problem class, so this is just a recording of what I went through today. Okay, so this first problem here is trying to understand the directional derivative from a city, Dubbo, in New South Wales to Sydney. So what we need to do here is we need to first of all draw a vector going from Dubbo to Sydney. So let's call this point here D, and this point S, Dubbo and Sydney, respectively. So what we're going to say is we're going to let this vector V equal the vector from D to S. And we want to have a unit vector. So whenever we're calculating directional derivatives, we need to have a unit vector. So U is equal to vector V divided by the length of V. So if we zoom in here, the scale on this map is actually given in hundreds of kilometers. So we can't, our unit vector is just going to be 1 kilometer, so that's not going to be very big. But you can actually see that a unit vector times by 100 in the direction of Sydney is going to look something like this. This is 100U, roughly. If we look at this scale over here, the length of that green vector that I've just drawn is roughly 100 kilometers. And so from here, we can estimate what the temperature is roughly in Dubbo. So somewhere between 27 and 30, say it's about 28.5 degrees C, because it's a little bit close to the 30. And let's call this point here P. And this we know is on a level curve. So temperature here is 24 degrees C. That means our directional derivative, capital D sub U, the direction of our unit vector U, of our function, in this case our function is temperature, at point D for Dubbo, is going to be approximately equal to the change in temperature divided by 100, 100 being the length of our, the difference here, so going from D to P. Okay, so what's that? So the change in temperature, the temperature at P is 24, temperature at Dubbo is 28.5, dividing it by 100, which gives us minus 0.045 degrees C per kilometer, or it's a little bit easier to work with, 0.45 degrees C per 100 kilometers. So minus 4.5 degrees C per 100 kilometers. So all this is saying is that as we stand at Dubbo, looking in the direction of Sydney, the rate of change of temperature per 100 kilometers is minus 4.5 degrees Celsius. Okay, moving on to this next problem here. We didn't get to go through this problem in class, but here we've got some level curves, and we were asked to sketch the gradient vector at a particular point, 4, 6, as shown here by this point on our diagram, for this function f, and we are asked to explain how we determined its length. Okay, so the first thing we know is that a gradient vector has to be perpendicular to level curves. So I can see that the gradient vector here is going to lie somewhere along this line. So I'm not going to draw a direction at the moment, but it's going to lie somewhere along that line there. And we can see that it's going to be going down to the bottom right because these level curves are going minus 1, 0, 1. So they're increasing, whereas above going up to the top left, they're going minus 3, minus 4, minus 5. So they're decreasing. So we know our gradient vector always points in the direction of steepest descent. So that's the direction our gradient vector is going to be pointing, somewhere down to the right. Okay, so we know that our gradient vector is orthogonal to our level curves. Our point that we're interested in, 4, 6, doesn't actually pass through a level curve, but we can estimate a level curve here. This level curve below is minus 2, so this is probably about minus 2.5, say. So that's where our point 4, 6 is, say, sitting on the level curve 2.5. And we can estimate from the left-hand side of this graph that the length of a unit vector is going to be approximately this length here. So 1 unit here we want to translate that across to this blue curve. So if I do that here, our unit vector u in this case is going to be about this long here. So let's call this our unit vector u. And we can say that our directional derivative in the direction of u for our function at 4, 6 is just going to be approximately equal to the change in our function, so delta f, divided by the length of our unit vector u, which in this case is just 1. So because that u happens to just about sit on this level curve here at -1, we know that the endpoint of our unit vector is -1. So we can write -1 here, and we're starting at roughly -2.5. This then gives us a directional derivative of 1.5. So that's saying that every step that we take in the direction of u, at that point, is our function increases by 1.5. And then to work out the length, well, to work out the length of our gradient vector, we just work out the length as we would for any other vector. And in this case, we know that our u points in the same direction as our gradient vector, because that's what we wanted in the first place. Okay, so in this case, this is just equal to our directional derivative of our function for this particular u. So all that won't be true if we choose a u in a different direction. In this case, it is true because it's going in the same direction. So this is just equal to 1.5. So our unit vector says length 1. So our gradient is going to be 1.5, so maybe about this long here. So our gradient vector of f at 4, 6 is going to have length 1.5 and be pointing in the same direction as u. Okay, this is one of the problems that we did go through in class today. Here we're just given a function. This could be describing a wide range of things, but it doesn't have any units associated with it in this particular case. We've got a function and we're asked to find the directional derivative in the direction of u, which points in the direction of some other vector. Let's call this v, which is root 3, 1. And what is the directional derivative at point 1, 2? So the first thing we need to do is calculate our gradient vector. So grad of f is equal to f sub x, f sub y, which is just 3x squared minus 3y and 8y minus 3x. And this vector v is not a unit vector, so we need to work out our unit vector. So that's going to be v over the length of v, which is just going to be 1 over the square root of 3 plus 1. So root 3 squared is 3, 1 squared is 1, times by our v, which is root 3, 1. So this is just root 3 over 2, 1 over 2. So that's our unit vector that we're interested in. We want to find our directional derivative in that direction. So we do du f of xy, which is just our gradient of f dotted with u. So when we do this, we get root 3 over 2 times by 3x squared minus 3y plus a half of 8y minus 3x. So this is just in any particular point x, y we might want to choose. So for example, what we're really saying here is you imagine you've got a surface and you're interested in the directional derivative in the u direction, and the starting point could vary. Okay, so that can move around, and so your directional derivative will change depending on where the starting point is, but you're always interested in what's going on in your gradient in that direction, or directional derivative in that direction, I should say. Okay, so du of f at 1, 2, this particular point, when x is 1 and y is equal to 2, all we do is substitute in those values. In this case, we'll end up getting root 3 over 2 times by 3 times by 1 squared minus 3 times by 2 plus a half of 8 times by 2 minus 3 times by 1. That eventually simplifies down to be 13 minus 3 root 2 all over 2. which is approximately equal to 3.9. So again, what that's saying is that at that point 1, 2, looking in the direction of u, our gradient is increasing by 3.9. So there are no units here again, but what we're saying is the height of our function is increasing by 3.9, whatever those units would be if there were units associated with that. Okay, the next problem here, we're asked to find the rate of change of this function at the point 2, 0, point P, in the direction from P to some other point Q. So let's just do a quick sketch of what this looks like. This is our x and y axes. This is our point P at 2, 0. And we're going up to some other point Q at 0.5, 2. So we want to find the rate of change of our function, in other words, the directional derivative of our function in the direction from P to Q. Let's call this vector here V, which is just minus 3 over 2, 2. So that's just working out our vector based on our terminal point Q, subtracting our initial point P. Okay, so remember we need to work with unit vectors. This is not a unit vector here, so let U equal V divided by the length of V. So if we work this out, we're going to have 1 over the square root of minus 3 over 2 squared, which is 9 over 4, plus 2 squared, which is 2, times by minus 3 over 2, 2, our vector V. This eventually cancels down. I'll leave the algebra to you, but eventually cancels down to minus 3 over 5, 4 over 5. Okay, so that's our unit vector pointing in this direction. So our unit vector U will say look something like this. It's our unit vector U. It's minus 3/5 and 4/5. Okay. Now we can work out our gradient as well. So grad of f is just df dx and df dy. So we have e to the y and x e to the y. So now we've got those components, we can work out part A, which is finding our directional derivative in the direction of u of our function at the point P, which is 2, 0. So we have our grad of f at 2, 0. So just substituting 2, 0 into what we found out up here, this gradient here, and then dotting that with our unit vector u, which we found above. So that's just 1, 2, dotted with minus 3, 5, and 4 over 5, which is equal to minus 3/5 plus 8/5, which is equal to 1. Okay, now we're asked then to work out the maximum rate of change, or rather what direction has the maximum rate of change at 2, 0. Well, we know that our gradient vector gives us the direction of the maximum rate of change, and then the length of that gradient vector tells us the maximum rate of change. Okay, so we know that it is our max rate of change is in the direction of gradient of f at 2, 0, which we worked out above is just 1, 2. So that's just this here. And this has value, the maximum rate of change, just equal to the length of the gradient at that point, which in this case is 1 squared plus 2 squared, square rooted, which is root 5. So if we were to draw this on, our gradient vector looks something. Okay, moving on to the next problem. So we've discussed this model for the spread of SARS. So here R0 is the expected number of infections per infected individual in an otherwise susceptible population. We have 5 times by 1 minus v, where v is the proportion of the population that's vaccinated, times by d over 1 plus d, where d is the average number of days an individual remains infected in the population. Now, we talked about this model previously in terms of public health control measures. So should you vaccinate more people, or should you try to quarantine them? We can also think of this R0 as a measure of evolutionary fitness from the perspective of a virus. And viruses can evolve, so they can evolve to escape vaccines, so they could decrease V, for example, or intuitively, they could also evolve to have a longer infectious period, so they might be able to evade detection, and therefore an infected person remains in the population for longer. So what we can say is we can expect natural selection to occur in the direction of the maximum rate of fitness increase. So all we need to do is work out our gradient. So our grad of R naught dV, which is just our gradient of partials, dr naught dt, dr naught dV, which are 5, 1 minus V over 1 plus D all squared, and minus 5D over 1 plus D. So we're asked, how do we expect SARS to evolve when D is equal to 4 and V is equal to 0.5? So what we need to do is substitute these values in here. So grad of R naught of 4 0.5 is equal to 1 over 10 minus 4. That's just substituting those values, 4 and 0.5, into our gradient function. Okay, so what's that saying then is we are expecting strong selection for vaccine escape relative to the infectious period, because here, although we've got selection for D to increase, it's relatively small relative to immune escape. So what we should generally expect is that there'll be very strong selection for immune escape and relatively weak selection for a longer infectious period. So we can also visualize this if we were to think about what our V and D space looks like. Obviously, V can't actually be negative, but what we can do is we can draw on the point for 0.5. So this is the point we're at here. And our gradient vector is pointing strongly like this. So although we can't actually end up with negative values, this is what our gradient is telling us, that we're pointing strongly in this direction. So we can see that we're mainly going downwards rather than going to the right, although we are going slightly to the right as well. So this is at 0.4, 0.5. Okay, the last problem on the problem sheet, which we didn't get to go through in class, was looking at how we can calculate the tangent line using a different method. Okay, so here we've got this curve, y is equal to x squared minus 3x, and say we want to find the tangent to this curve at this point here. How do we do that? Well, we could do it in the usual way that we learned about previously in Math 154. We can also do it another way. So if we now think of this as rather than being a curve, which is just a function of one variable, we can let f of xy equal x squared minus 3x and then minus y, so just taking the y to the other side. And then this curve here, this is now just a level curve of our function with f of xy equal to 0. Okay, so if we now calculate our gradient, so grad of f of xy, that's equal to 2x minus 3 and minus 1. And because this is orthogonal to level curve, it's going to point away like this. So grad of f of xy, in this case, grad of f2 minus 2 is going to point away like this. We can just substitute our values in. So grad of f at 2 minus 2 is just going to equal 1 minus 1. So this gradient vector here is just 1 minus 1. Okay, so how is that useful? Well, we know that our tangent line is also going to be orthogonal to our gradient vector. So our tangent line is going to satisfy the grad of f at 2 minus 2, dotted with a vector v that goes in the direction of our tangent line. So let's call the vector v some vector here, v, which is at some point x minus 2, y plus 2. The reason it's minus 2 is because our x coordinate of this point here is minus 2, is 2, and the y coordinate is minus 2. So any point we go to along this line. So if this point here is xy, the vector from 2 minus 2 to that point y is going to be x minus 2 and y plus 2. So if we know that this is going to be a rectangle here. So if we take the dot product of our green and our blue vectors here, this has got to be equal to 0. So if we substitute those in, we now have 1 minus 1 dotted with x minus 2, y plus 2 is equal to 0, which eventually simplifies down to be y is equal to x minus 4. So this has given us the equation of our tangent line in a completely different method to how we would normally derive it. It's not as quick as doing it the other way around, which is why we don't do it this way usually. But by applying some of the techniques that we've learned here, we can think about our tangent line in a slightly different way, in the sense that we can think of our function of one variable as actually being a level curve of a function of two variables, using the properties that we've learned about gradient vectors allows us to then generate a tangent line. So it's just a different way of approaching a problem. Okay, all right, thanks everyone. I'll see you at the next problem class.